Okay, so I think, yeah, I can see it's recording now. So this is part 2 of the video today. We're just gonna, I'm gonna share the screen for the code. And I just want to do a couple more things, right? So wrap it up really, and then we're gonna get into some of the slides to kind of go over topics. Next week, next Tuesday, I will do the CIFAR problem, which is now gonna be 70,000 samples. We're going to use a data set of images in color. We're obviously going to build. So today you built your first neural net, right? A multi-layer perceptron, just one hidden layer. Next week with the CIFAR 70,000, the inputs are much larger. Images 28 by 28. I think we're going to do deep learning. All right. So that means just more layers. Okay, but you already intuitively know how to do it. All right, so today let's just wrap up this code with like I said, a couple more things. So let's go back into it. So I'm sharing the screen. So I'm going to be clear here. Let's bring up our code again. So simple neural net. So the simple neural net here. And now let's try to do a couple of things. So let's just print out some data, right? So the first thing I'm going to try to print is from the model parameters, right? I'm going to print out some of the data, right? So let's see what we can get out. So the beauty about using the NN module is that it's not like when we did the equation, it was just an equation. Now those equations are really objects themselves with a lot of metadata around them. So we can print out a lot of information if we need to. All right, so I'm gonna do here parameters, right? And so from model parameters, so let's say for param in model parameters. Okay, so from it, let's try to print out some things. Notice I'm doing a list comprehension in here. So the first thing, let's look at the shapes. And let's just, now this is information that may be useful to you, or it may not be useful to you, right? As you start building projects, etc., you want to just get as much input as you can. So let's go ahead and run this one. Control X. All right, and then you can see we've got some of the information there on the parameters that we have available. Oh, wait a minute. Which one am I using here? That's a good question. Yeah. All right, so that's the linear model, which kind of makes sense, right? For it to be the linear module. So now let's do the one hidden layer. That's the new model, right? So let's go ahead, Control X. Oh, sorry, that's gonna error out, unfortunately. Okay, Control X, Y. And it's a little bit slower, but we can see in a sec. Now, while we're waiting, we can see here when we printed the function, it actually also gives us a little bit of information about the architecture of our model, right? When we did that print. All right, and there it is, 13 and 1, 13, 1 and 13, 1. Right, so these are the, basically it's like we're looking at the weight vectors, right? So the weight matrices that are here, 1 and 13, 13 and 1, right? And we're viewing that information in there. So that corroborates things. We have this as well. Now, do you guys notice something else in this output? What do you notice? Look at those validations, those losses. Huh? What would you say about this one? Are you still that linear is better? You're less convinced now, right? This can happen too, okay? Because remember that when we initialize data, the data is what? Randomized. So this time around, when we did the training, it learned better. So then you might ask me, so, how do I pick one? Well, you have to experiment a lot. Eventually, though, you'll find a tendency. This is where your statistics classes come in, right? And that mindset of, finding the distribution, finding the pattern, right? So here it did a little bit better, right? At least a little bit more, less surprising or less shocking. This one is pretty precise. And I could argue that it's still not great at generalizing, right? But you can see that it's a little bit different. So that's why you should try multiple experiments, trying it 10 times and seeing what it does out of the 10 times. You guys see that? And that's what it's going to be like, because it's never exact. But eventually, though, as I said, there's going to be a tendency towards which it is going. All right, what else do we want to try to print here? You can name. I'm not going to cover the aspect of naming the nodes in the computational graph, but you could if you wanted to. All right, so let's see here if we can just print out some information about the computational graphs. So let's go back into the code. Here. So let's do another print statement. Print. And it's going to be another list comprehension. But this it's pretty similar. This one will just be for param in model parameters. Let's find this. So, and let's just print out param. Now, not all of this is going to be useful, but I just want to show you what you can do. All right, so param, print out param for param in model parameters. Let's run that one. Notice here that the validations are actually, the validation losses are actually better now. And now they kind of diverged again. You see that? And that's what it's like. All right, and you can see here now it's printing out the actual tensors, right? So that's what we want, we kind of looked at that. Okay, so that's what we requested. And this, you'd have to dig deeper into this and what it is, okay? It's probably the weight vectors that are being printed out there. So those are probably the weights, but you'd have to kind of experiment with that. And then the last part that we want to do is let's try and predict. All right, so let's try and predict. So let's go back to the code. So what do I mean by predict? If you remember, when we do this, right, we have train TU normalize, validation TU normalize, train TC, and val TC, right? So we have these parameters. So we can actually try to predict something and compare the output. So we're going to compare. So the validation data we have, so actually this is better viewed up here. Yeah, so we have our validation data, train, and then we have TU and TC. The equation was that given a TU, we get a TC, right? That's basically the idea. Given a TU, we get a TC. So we're going to take now the validation TU, run it through the model, and it'll predict what the corresponding TC should be. And then we're going to compare those with the real validation TCs. Does that make sense, guys? Yeah? All right, so we have a model, right? You agree that the model is now trained. So now we're going to run the data through the model, get some predictions, and compare the predictions to the real. So that's really the last thing that we're going to do with this. So I'm going to go over here and create this function. Okay, so let's call this predict. So that's really what you want to do whenever you build a model. You don't just want to look at the losses or whatever. You actually want to look at, get some predictions. So in this case, notice how simple it can be. We're going to say pred or predicted, comma, model val t u, right, norm. And also we're going to print the real data, which is going to be val t c. Does this make sense? So we're just running the data that used through the model, getting the C's basically, and comparing it to the real ones. So let's go ahead and run that one. And this is with the multi-layer perceptron is the one that, that's the model that we're using basically. Our multi-layer perceptron or our neural net, simple neural net, to give us some predictions. So what would we expect by looking at these losses? I would expect it to be somewhat close. Notice we're still not doing any kind of accuracy or anything like that at this time, but we're just looking at, because we only have 13 samples, so visually it's easy or possible to assess. Okay. Oh yeah, we only have two, that right? We only have 2 out of 13. We only have 2 test samples, correct? Am I correct about that? Yeah, I am, right? So out of 13, we only have 2. So that's why we're only seeing 2 here. So we see 15 and 2. That's the predicted. The real one was 13 and 0.05. So just by looking at this, what would you say? How would you grade that model? What do you think? Huh? Right, but the first one is 15.4, the real one is 13. That's not so far off, right? And then the other one is 2. This one is 0.5. It's also not that far off. So it seems like the model did learn. Obviously, that's not good enough as a metric of learning, but it's a start, right? It's a start. This shows us that the model learns. This shows us that, you know, that, and that's basically the idea. Going forward, obviously, we're going to have more samples and we're going to need more efficient ways of evaluating performance. Do you guys see that? Going forward. So this idea of adding the prediction function at the end is going to become very useful. And we're going to have to start adding things like how to measure real performance when we have 10,000 test samples to look at, or validation samples. All right, great. So that concludes this code. And now what I want to do is really just go over the slides. I think we've spent a lot of time on code to where you have an understanding of how to craft this. Now I want to get into some of the ideas and concepts of this terminology. And then next Monday, as I said, we will be ready to do the CIFAR, which is going to be, what's going to be is no longer a linear regression. It'll be a classification. The inputs are going to be much larger because it's going to be images that are 28 by 28, where we're going to treat every pixel as an input. So we're going to end up with like 784 features instead of just one, as we had it here. And the outputs will probably be between 2 and 10, depending on the number of classes that we end up using. Is it a dog? Is it a cat? Is it a plane? And so on. Does that make sense? So was this clear? Did you guys understand this idea of the template? Did you understand this idea of, you know, the loss function, the architecture? Are there any questions, I guess, before I close this code and we move to this, to the Brightspace and the slides? Any questions? Making sense? All right. Well, I'm not hearing any questions, so it sounds like you guys are getting it. All right, great. So I'm going to exit out of here. So I'm just going to do clear. And we're going to, let me switch over. And let me pause the recording.
In progress.
All right, so it's recording. Let me share the screen. All right, so that should be the slides. All right, so as I said, so this is just now, we've talked a lot about the code and, you know, and you've seen a lot of the terminology. So now this is kind of a, you know, it's slides with a lot of information in them. And so we talked about data sets, right? So let's start there. As I've said, data sets are really, you know, like, I don't know, somewhere between 60% and possibly 80% of the work. I know it doesn't seem that way right now, but you'll see later. So, you know, the way I'm doing this class this semester is I'm trying to cover a lot of the machine learning modeling part first with PyTorch. And then during the second half of the semester, it'll be you getting, and I'm providing the data sets, but in the second half of the semester, it'll be you guys getting the data. So you've seen a little bit of a taste of that with the first homework assignment. I honestly do that homework assignment just to see your skill. You know what I mean? That's ultimately what that homework is. You know, everyone submitted it now, and nobody really I'm not going to accept any more homework for that. I usually give everyone full credit for that, but it's really like a little test just to see your, I want to see how you solve that problem. So but going forward though, in the second half of the semester, we will have to get the data. All right. But it makes sense to learn all the models with like clean data sets that are already in the right format, so you can understand how all that works with data sets already set for machine learning, so that later you have an eye for how, okay, now that I have raw data, how can I get that data into those same formats that I know? Does that make sense, guys? That's kind of the best approach, I think. So in a sense, it's like you have a model, you'll have eventually, let's say that you took this class in a deep learning class, you have a ton of models already built with tons of different data sets and how they take that data. And then when you encounter new problems in your, in your work, then you would take that raw data and convert it to those formats. And then boom, everything else hopefully should work very well. All right, remember that what we're doing, the code doesn't, another thing that's great about what we're doing is that the code that we're writing works both on CPU and GPU. So it's not like you have to reprogram it totally different for GPU. You barely have to make maybe a few slight modifications here and there. And keep in mind that as these libraries keep getting upgraded and upgraded, they just make that transition even more seamless. You see that that's the goal, right? And so that's the idea. But in essence, data sets, which is where we started, are a lot of work, and you'll see that later, right? And even now with the data sets that we have, you have seen that there's quite a bit of pre-processing. We do a lot of normalization, we do a lot of cleaning the data, etc. Make sense? So in essence, data sets are central to machine learning, right? So, data sets are central to machine learning. Obviously, it's called learning for a reason, right? We don't deterministically write the programs, but we instead write algorithms that learn from data. And in theory, they could learn from that data forever, right? That's the idea. So that the algorithms are data hungry. So as you saw today, we had like 13 samples in our data set, and that's just, it's kind of nice to start with something that you have control, right? You can see a big picture of the data. Next week, though, we start now with, or next Monday, we will start with 70,000. I think it's 60,000 for train, 10,000 for test, something like that. The CIFAR. I used to do MNIST a lot, and a lot of people did MNIST, but they thought that MNIST was not sophisticated enough because it was just grayscale numbers, right? So nowadays, CIFAR 10, it's a little bit more sophisticated, it's RGB, but still similar to MNIST that you can use it. So we'll be using 70,000 in total. Obviously, that's by no means big data. Big data would be millions of records, or even something that you measure in terms of terabytes, right? Not really even in how many records, but just the amount of data that you're using. This question, what is better to have, the most powerful machine learning algorithm and small amounts of poor data, or lots of data, even if our algorithm is not the best, right? So there's this idea, and really the answer is the data. Data is king, okay? So the algorithms, I honestly would say that you're not gonna be modifying a lot of these algorithms. It's really, as I said, it's really about looking at all the algorithms, knowing the data sets that they take, and then you're gonna use that same tool all the time, right? And what's really important, you're not gonna be modifying that algorithm, or you might change the architecture a little bit here and there. But in essence, what is really important is that you wanna have data, good data. And that means not noisy data. For instance, the good example that I like to provide, that I'm going to ask you probably to do for your project, is collect Twitter data. Twitter is a very noisy medium, so try to do anything in Twitter, any kind of classification or analysis, and you're going to end up with a lot of data that's not very useful. All right, and so you have to clean up that data, etc. And so that actually takes us to the reason of why do companies like Facebook and Google do so well? You know, what's the thing that they have? Well, if you think about it, what they have is they have tons of data, right? Facebook, think about how many people are on Facebook every day, typing things, liking pictures, right? Same in Instagram, Google. You do all these searches and then you select one of the results, etc. So they collect a lot of, and then there's your private information that they also collect. So they have, they do so well because it's not really their algorithms that are so great, although they are inventing new great things, right? I think it was it Google that put out like transformers and then BERT and all these variants of it. So certainly every now and then they do come up with some amazing algorithms, but it's algorithms that you end up using, right? But it's really the value that they have is that all this data that they can process. Okay. Right, and then this you can see. All right, so characteristics of data sets. So we looked at this, right? We basically read some data. When you're thinking of data, we thought in terms of a matrix, right, or a vector. And the key term that we were calling these is tensor, right? So in the beginning, as I said, I'm kind of doing a review of everything what we've done. So in the beginning, we looked at this idea of the tensor. We spent a couple of weeks just on the tensor itself, and then even now we're going to continue. But the idea is that we're loading our data in terms of rows and columns. Okay, rows and columns. We saw this function from NumPy load txt data set, specifying the delimiter, skip rows. And then we saw that we usually read in the data from the CSV, but then we split the data into two, right? X and Y. You remember that? And remember, whenever you get confused about this, I always just do this. This is central to my understanding of everything that we're doing, right? So when we read our data, we want to have our X, right? In this case, the X could be a matrix, and usually this is going to be some kind of a vector or something like that. It could be a matrix as well when we look at something called one-hot encoding. All right, so this is slicing. So what are we doing here? We're basically, the colon, remember, means all the rows. And then this means a range of the columns from beginning all the way to 4 without including 4. And then this one would include the 4th column. Okay, make sense? All right. So here we have an example. The two classic, or the examples of data are IRIS, of data sets are IRIS, MNIST, and CIFAR, right? That we are basically going to be focusing on. These are very academic data sets, but they're very useful to understand the concept. So it's good to just understand these data sets and what they are. So in the case of IRIS data set, is a collection of multiple variable analysis data. It contains a total of 150 samples, right? And there's going to be 3 classes. So basically, out of the 150 samples, 50 belong to the class Setosa, 50 belong to the class Versicolor, and 50 belong to the class Virginica. And those are basically species of plants. So it's basically somebody measured like 150 samples of plants. And that's just one of the classic data sets that we can use, right? So you'll see me reference this data set either in exams or just in general. What's important to me is that you know the terminology of what everything is. So the data set usually comes in like this, right? It looks like this. And if you notice, there's one column, right? Another column, and another column. So it's basically 4 columns. And those columns are the features, right? So if you look, X1, X2, X1, X2, X3, X4. Do you see that? That's So basically, if I ask you, for instance, what is the size of Iris, that data set, we'll see it at some point. It's 150 by 4, and it's got also that's the X and the Y. So sorry, this is X. So 100 and so these are called what? These are called samples, right? These are called the X's, X1, X2, and X3 and 4 are called features, right? And these, the Y vector, are called labels. Okay, so in this case, notice that it's 0, 0, 2, and there's probably a 1 in there. So there's 3 classes. This is a 3-class problem, 0, 1, 2, like that. And those represent setosa, versicolor, and virginia. Does that make sense? Okay, that's a common classic data set that you'll see me reference quite a bit. Then we're going to have MNIST, and MNIST is going to be a data set similar, except that it has a train set and a validation set kind of built in. This one goes from 1 to 60,000. This one goes from 1 to 10,000. And the number of features is 784. Okay, and then the labels, it's going to have a label associated with it. And the labels go between 0, 1, 2, ... 9. So there's 10 labels basically. And the MNIST data set, whereas IRIS is for plans, the MNIST data set is for handwritten digits. So they're basically pictures in grayscale. So they're not RGB, they're not in color, they're only black and white. So they're going to be like handwritten. So some people write the 2 like that, others write it the other way. It's going to be a 7 like that, 7, 7, 5, and so on. So they're basically pictures of images. Okay. The other, so that's MNIST, and we'll be looking at that one. And then the other data set is CIFAR. I think it's called CIFAR 10. And this is going to be, you know, a little bit more complex because it can be viewed as it's RGB. You see that? So it's going to be still 60,000. It's very similar to MNIST. So it's going to be 60,000 for training, 10,000 for validation. But now this got the RGB component, which means it says 1, 2, 3. It's got 3 channels, right? And then the dimensions are going to be very much like MNIST. The images are 28 by 28, so basically 784 for 1, but there are 3. You see that, guys? Okay, so these are data sets. Let's do here. Let's think a little bit about how we're going to process images, because that's what we're going to be doing next week. Let me just add on here some slides. All right. So one important thing about what we're going to be doing is when we have a neural network, right? So let's think about what we did today. So we had Celsius and Fahrenheit, right? So we had Celsius and Fahrenheit. This was the X, the feature. This was the Y, right? That we were predicting. And when we created the network, it kind of looked like that. It was a 1-to-1 because we had 1 input and 1 output, and we had the weight there. Do you see that? Now with the images, it's going to be a little bit different, right? Or actually, let's do it now IRIS, right? So with the IRIS data set, if we look at IRIS before, you can see now it's got X1, X2, X3, X4. What are these? So let's say we grab this one, right? So that's the plant, some plant. Let's say class is whatever, setosa. So then what we're doing here is we're representing that plant with these 4 features. We're saying that the plant is 4.9 of, I don't know, the leaf length, 3 point something of something, or the root, also another measurement, 1.4 of the stem, something that we measure in it, and 0.2 of maybe something to do with a chemical or pH or whatever it is. Do you see that? But we took 4 measurements from that plant, and those measurements, we said, okay, we took these 4 measurements. That is this type of plant, Setosa. How do we feed that into the network? Well, the network now that you know a little bit about architecture, you know that this data set, it's like this, right? So instead of just being Y and X, it's going to have a Y, but it's got now several X's, X1, X2, X3, X4. So what does the network look like? Well, in its simplest form, now we can't just have 1 neuron, we're going to have 4. And this is important for the architecture. For the architecture of it. We're also no longer going to predict just 1 output value. We're going to predict 1 of 3, Setosa, Virginicar, versicolor. So actually our architecture will start to look like this. Okay, do you guys see that? And so the question is, as we start building our neural nets, NN, right? Then, if we only do something like this, right? It's not really, it's kind of a linear combination, right? A type of linear combination. But if we start adding layers, just like we did today, we can create a multi-layer perceptron. So for instance, the same 13, right? ... 13, we have 4 inputs, 3 outputs. Do you guys see that? And basically for iris, just like we did for today's linear example, we can take our data, and our data is going to determine what the architecture looks like. Actually, the middle part is exactly the same as what we did here, but the input and the output are going to be different based on exactly this. The number of labels usually, and the number of inputs in the feature vector. So here, this is 4, because there are 4 here. Is this clear, guys? Very important for your, so when you did that nn.linear, right, that you did, remember, we did 1 and 13, right? So what would it look like here for iris, that first layer? What would it be? It was 1 and 13 because there's 1 and 13 here and 1 output, right? But here we have, it's different now with iris. So what would this look like? Huh? What? 4 and 13, exactly, 4 and 13. Do you guys see that? That's how architecture is determined. Got it? All right. Let's take a look at MNIST, or so let's take a look at MNIST or SciFarm. So with MNIST, we have a data set that, again, it's going to have Y here, right? So that's going to be Y. And then this is the X data. There's going to be 60,000 samples, 60K. And how many features? Well, the features now, it's a little bit more complex because we've got images that are 28 by 28. 28 by 28, right? And so how do we represent this? So this is, let's say, MNIST. So we're doing MNIST here. So it's a 7. There are 28, the picture is 28 by 28. So now we're used to feeding a vector. If you think about it, we're feeding a vector. So I said this had 4 for every sample. So this was 4. But this image is 28 by 28. So the easiest thing now to do is to take an image and spaghettify it. You know what I mean by that? Imagine like you grab one end and the other end and you just pull it like that, and making it into a vector. You guys see that? So for instance, here, you know, imagining we have this and then that and then that and so on, right? So what we would want to do is convert this into a vector. And so we just grab the first one. Let's say there's 1, 2, 3. So we're just going to put in 1, then we take 2, then we take 3, and so on. And we kind of make it into a vector. Do you guys see that? So basically, that's why when you have an image that's 28 by 28, you can just say it's 784, because that's 28 by 28 is 784. Is this clear? Now, this is the easiest way. It's not necessarily what we're always going to do. We can actually feed the images 28 by 28 if we think of more advanced deep learning things. But for now, this is the best concept to understand. It's very easy, by the way, to do this with Torch. It's something basically like reshaping. You might have something that looks like, let's say you have 60,000 images. So 60,000 images, right? And they are 28 by 28. Sometimes if you want to just reshape it, you do something like 60,000 minus 1, right? And then when you do this, it just figures out how to convert this into one single thing. So it'll do the whole spaghettify thing for you. We'll see that in the code later. Make sense? But we end up with this. So now how do we build a neural net? Let's say that we want to build a neural net here. Still stay with the 13 for now. So we need to define how many inputs we're going to have and how many outputs we're going to have. All right, so in this case, this has 10 classes, right? So one way that we can do it is we define 10 neurons here for the 10 classes in the output architecture. Make sense? And this directly affects what we were doing today, right? If you remember, the output was also defined. In our case, it was 13, 1, remember? Because there was only one output neuron. But in this case, it could be 13, 10 to indicate that there are 10 classes. And that's one of the ways of doing it. Now, the question is, what would be the input here? What would be the number of neurons in input? This is output, and this is hidden 1. What's the number of neurons here for the MNIST example? Anyone? 784, right? So we need to have 784. Perfect. So when we create, again, the NN linear, NN.linear, it's going to be what? 784, 13, because that's what we've defined to have in the hidden layer. Now, should it be 13? What do you think? More than what? That's a good question. Should it be more than 784? Remember what I said. This drawing, in general, you want to have a funneling type of behavior. So technically, you don't want more than 784 in theory. You see that? And the idea, again, is force the model to learn with less. Otherwise, it'll start learning strange things. It's like honestly, it'll start philosophizing about it, right? So you don't want to have that. Instead, you want it to be more precise. You know, well, I only have these many resources. This looks promising. I'm going with it. And it does, actually, in a very real way. That's what it does. So if it's not 784, but not 13, what should be the number then? Huh? How many neurons? How many? 500, 600. Okay. Yeah. Why not? And that's based on what? Well, there's no science for that. There's no science. That's really why you should just practice and look at models and experiment. If we have several layers, you probably want to make one that's 500, one that's 300, one that's 100, and so on. But intuitively, you want to funnel it as much as possible. that's kind of the idea. Does that make sense, guys? It's an important concept. All right, good, good. And then, as I said, we haven't looked at more hidden layers, so I don't really want to introduce that yet, but you might expect that we will have more, okay? What would that look like? So that would look like, what we did in the sequential object. So we did linear, right? And then we did 784, and then let's say 500. And then we do the 10, correct? Because remember, it's basically the results of this linear, you want to run them through an activation function that is nonlinear, like ReLU or something like that, 10H. Now, let's say that we want to add another layer before the output layer. Right? It's also going to be a 10H. And then we have the basic output. And in the output, let's say is MNIST, so there's 10 classes. And we're going to do let's do sigmoid just for fun. So this one, would you agree this is the 10, right? That's the 10. So if I gave you this on the exam, this code, how would you draw the neural net? So what do you got to do? You have to go over here. And then, there's an input and an output, right? So how many in the output? There's 10, correct? All right, so there's 10 in the output. What about in the input? How many are there? 784, perfect. And then there's these tangents. And then how many hidden layers do you have here? Huh? 2, right? 2. The first one is already drawn for us. How many hidden layers in the first one? What? 500, right? 500, perfect. That's this one, right? So we need to define this one. So this one is basically, let's say this is hidden 1. This is going to be hidden 2. So we need to start from here to here, right? We got to make that transition. So that means this value is probably going to be 500. Why 500? It's this 500. Do you see that, guys? And that's going to be the standard approach, as I said, in TensorFlow and PyTorch and Keras and all of them. They kind of follow this intuition. Now, what about this value here? 400, why 400? Yeah, no, I'm not saying you're wrong. I'm just saying why not 200? Why not 300? Why did you choose 400? Right? So yeah, so I would probably say maybe 200, just limit it even more a little bit. So 200. And so this is going to be then 200. Do you see that? It's still a big jump from 200 to 10, right? And so what about this value here? What is that one going to be? 200. Very good. And then 10. Do you guys see that? That's architecture. So you just build, that's how you build these neural networks. So, we started with a very simple one, linear, right? Which was just, remember, it's difficult to see it, but actually it was only one X1, one Y1, and one W1. And the bias, of course, there's a bias, right? This one is a much more complex architecture. This one is because there's, now before, what we did today was just that, right? With 13 of these, but it was only what is called a multi-layer perceptron, MLP, all right? This one that we haven't yet written in code, we'll probably do this on next Monday, is a deep neural network, DNN. Deep neural network, and basically, it's deep learning. That right there is deep learning. Got it? And if you want it, so I think now intuitively, if you wanted to do more of these, you can pretty much figure out how to do, I could tell you do 5, do a deep neural network with 5 hidden layers. And all I have to tell you is the number of inputs, the number of outputs, and then we can, you can start to craft it. That's why this is called architecture. It's like you're the architecture. You're the architect. You define, the structure that this is going to follow. Now, is it necessary that, or is it necessarily true that if you have 10 hidden layers, that deep neural network is going to do better than one that only has 3? No, it doesn't correlate that way, right? So you don't need to have more layers in order to have better performance. In fact, there's like a graph that's going to eventually plateau. So if you think, what's this thing? Yeah, so there's going to be a graph like this. It's going to improve until it starts to go down. Or it could also take way too long a lot of layers means millions and millions of parameters when you're talking about really big things. Okay. Got it? There's a deep neural network called a transformer. I think it ends up having like a simple one has like 3 million parameters to calculate. A lot. So it can be very slow. It can take 12 hours. Just to, so Google runs these things for a month, right? So it's a lot. But this is a pretty important thing, an extension of what we did today, just to kind of get a better feel for how this works, okay? And then, as I said, on Monday, when we do the SciFAR 10, we'll hopefully explore deep neural networks in a little bit more depth. All right, so that's basic. Now, I don't want to get into the data sets that look like this one. The RGB right now, they're a little bit more complex, but just be aware that that's why these are tensors, okay? A tensor, remember, by definition, is a hyperdimensional matrix. You can have as many levels, a cube, a hypercube, etc. So you could literally load the images as cubes that are RGB. They could be video, they can be, so a lot of things are possible. It's just more complicated, obviously. For now, I don't want to get into that complexity. And I think this is a good, level to be at, this idea of spaghettifying your images, right? Spaghettify the images, get a feel for how that works first. Any questions about anything that I've said? Oh, all right, good. So anyway, that's kind of the idea. There are obviously other things with data sets. Dealing with natural language text, like phishing data, for instance. So you guys have actually tried to do something with this one. You've submitted a homework assignment, so I'll take a look at that now. It was due last Wednesday, I think, the last day. So I'll take a look at that. You have a homework due today also on linear regression. Images, of course, are another data set. That's the next one, SciFAR, that we will look at. So certainly, the advantage, I actually don't work that much with images. It's not really my interest, but certainly it's good to look at image data sets. It covers a lot of the concepts really well in an intuitive way. And so we'll also take a look at image processing. There are other ways that you can get data, like speech processing, but we're not really going to cover any of those. Network intrusion data, and so on. All right, so features, what are features? So I asked this to you guys. Keep in mind, we will have an exam at some point, right? We're currently on week 6. So actually the exam will be around week 8 or week 9, right? I'm not sure because we have fall break in there. So if fall break is actually, I think we have this Monday and then is fall break, right? So probably the exam will be after fall break, that Monday, okay? Start thinking about that. So understand the terminology really well, right? So features, what are they? Well, there are ways to represent the sample, okay? In the vector space model, the features actually represent dimensions in the vector space. So what that means is, for the iris data set, how many dimensions do you have? How many features do you have in the iris data set? Huh? 4. Okay, so features are dimensions in a vector space. So therefore, what's the size of this vector space? What's the n? The dimensionality of this space? Not 3. 3 is what you can see. As far as you can see, as far as the eye can see, you can see in 3 dimensions. But if you have 4 features in the iris data set, what is the dimensionality of that vector space? 4. So that means there's an extra dimension. Now we can't really map it, but just keep in mind, this one is what is called orthogonal, which basically just means at a 90-degree angle from all the other axes, which means it's independent. You know what I mean by that? So for instance, I have one line, right? I want to create an orthogonal dimension to it, or rather an independent dimension to it, or a 90-degree dimension. Well, I just do that, right? And that works. Then if I want the C value, this one would come out to me, right? And then it's going to be 90 degrees to the other 2. Obviously, I can't draw that like that, so I'm just going to do that. But just keep in mind, it's orthogonal or 90 degree. You can keep doing that in math, okay? And that's, so basically then I can throw in other dimensions in there. So iris has, so basically what you do is you say you're right, it is R4. So what about if I asked you for the MNIST data set? When we spaghettify it, it's got 784 features, correct? The data looks like 60K 784, right? So then if I draw the vector space, how many dimensions does it have? 784, perfect. So it's R784. What does that mean? It means there's 784. Obviously, I can't draw all of these, but of those. And they all follow the property that I just mentioned, that they are orthogonal or 90 degree, intuitively speaking, from the first one. And from each other. They're independent, and that's good because it provides like geometrical metrics and principles, right? So the principles of geometry that we observe here in this 3-dimensional space, they also exist in these higher dimensional spaces, mathematically speaking, although we can't visualize. Got it? Make sense? All right, so that's good. So that's called a vector space model, right? So the vector space model is whenever you do something like this, okay? But that comes from the features themselves. Questions about that? All right, good. Types of features. They can be binary, continuous. You actually did this in your homework, right? The bag of words approach. What type of features were those? The homework 1. Binary, right? You had a word 1, word 2, all the way to word n, and you would literally say 1, 1, 0, right? They're either present or not present. That's a binary type of a feature. A continuous feature would be something where it's like setosa, right? And it's, you say 2.8, 3.7. Keep in mind, this is very important. Now, there are 2 types of data here that are really important for you to understand. There's the data that is nominal, and it's data that is not really related in a scale, and the data that is related in a scale, continuous in a sense. So for instance, let's say that I say, when you do machine learning for these tensors, right, you can't just put in, let's say that you want to look at a city and you have, for whatever reason, one of the features is cars, right? Cars that they have in that city, right? So there's 10 types of cars, right? So there's going to be like Ford, Toyota, Mazda, you know, Mercedes, BMW, right? So 4 different brands there. Okay, but we can't really write letters, right? So that has to be converted into a number. So let me actually here use the eraser. So this has to be a number. And then now, oops, no, sorry. And now, so the numbers just arbitrarily, I'm going to say 1, 2, 3, 4, where 1 is Ford, 2 was Toyota, 3 was Mazda, 4 was BMW, right? Now, you have to be careful here because we didn't intend to say that Ford is somehow number 1 and Mazda is somehow number 3 and BMW was somehow number 4. We didn't intend for that. That was just arbitrarily assigned, right? So there's a difference there in that type of feature versus, let's say, W3, and you have something like age, right? So here you have, you know, one customer, one user is 17, you know, one is 50, you know, one is 30. There is a relation, right? You know, a meaning or a price, or it could be whatever. Do you see the difference, guys? This is an important thing when you're dealing with features. Okay, oops, sorry. When you're dealing with features, they're both numeric, but only one of them has a meaning in terms of an axis. Okay, like in an axis, age is important, right? Because, you know, the people, you know, you have 2 groups, right? Younger people, older people. From a marketing point of view, that's probably really important if you're trying to sell them, I don't know, whatever, right? But on the other axis, the axis of cars, we got Ford, Toyota, Mazda, BMW, right? There is no such thing as that relationship there, right? One, you know, is non-existent. So you kind of have to be careful when you look at those features that way. But you can still just represent a matrix like this and experimentally see what happens. But in terms of individually comparing, it becomes a little bit more tricky. Does this make sense, guys? So actually, how do you deal with, so statisticians will have a serious problem with this, and they will recommend that you actually need additional processing. Their recommendation usually is leave this one as is, this feature, but change this one. Don't allow this one to remain actually, and instead convert it. And the way that they convert it is they convert it into a binary representation. So what that means is, let me open up a new one here. This is an important thing that I think you should know from the point of view, lest you have some statistician in the room that's going to give you a hard time at some point. Believe me, I've had that happen to me. So what do I mean by that? I mean that if you have this, I'm just focusing in on one feature, F3, for Toyota, no, sorry, what was Ford, Toyota, Mazda, BMW, right? You really need to use your programming skills or NumPy or whatever to convert this F3 into features that didn't exist before. So new features. So actually, let's say F31, F32, you can name it whatever you want, but this is just an example. F33, F34. So technically, Ford, Toyota, Mazda, BMW, which were one feature of 4, now becomes 4 features, and they're just binary now. Do you see that, guys? Because that's there, because as I said, there was no real relationship here in this data, so you really do not want to maintain that in your vector space. It's you know, a lot of people would say that's not correct, and so what you do is you kind of transform the 1 into 4, and so now this becomes this thing where if it's a Ford, You see that? If it's a Toyota, if it's a Mazda, and if it's a BMW, oops, sorry, like that. Make sense? Yeah. So this example actually applies, if you notice, I was applying it to the features, the X's, right? But as it turns out, you also at some point may need to apply this to the Y, because it's a similar idea, and the Y's are what? The labels, right? So in the example of, let's take the example of Iris, which only had 3 labels, Setosa, Virginica, and Versicolor. We had 0, 0, 1, 1, 2, right? Those are the Setosa, Virginica, and Versicolor. Again, sometimes we need another representation of the labels. This is called one-hot encoding. Oops. Oops. One-hot encoding. All right, that's pretty important also to do. And we'll finish with this. And the idea here is to do exactly the same thing. You figure out the number of labels. So how many labels do we have here? 3, right? 3 labels. So they're not features anymore. They're like Y1, Y2, Y3, something like that. So now, if it's 0 in this representation, it's going to be 1, 0, 0. Do you see that? For the next one is 1, 0, 0. What about for the next one? It's going to be 0, 1, 0. The next one, 0, 1, 0. And the last one, 0, 0, 1. Is that clear? So these are 2 cases when you may need to do that. It's just something you have to do. So again, for the features, it's when you have like BMW, Ford, etc. There's no meaning in that number. So then that might be a better representation. And with the labels, because as I've been saying, why is this necessary? Well, if we're going to represent our neural network like that one, this one has 10, right? 10 neurons, right? Then if you notice, the output is a thing of 10. You see that? It's a thing of 10. So our labels can no longer just be a thing of 1. They will need to be a thing of 10, a vector. Do you see that? Is this clear, guys? All right. So it sounds like this is clear. All right. So I think we can stop here for today. Stay if you have any questions. Otherwise, make sure you finish the homework that's due tonight, and I will see you guys next Tuesday, next Monday, when we will go over now a deep neural network with CyFAR and everything like that. All right. So if these recorded correctly, I will post them